Hello and welcome to our channel again. So in this video I am going to discuss the part 2 of the quantum mechanics, which is the normalization and expectation values. And in the first video I have discussed about the quantum operators and how operators acts on the wave functions to gives us the different types of quantities. So here I am going to discuss about a very important concept that we have learned in the quantum operators is the expectation values, and also a concept normalization, which is a very important concept and a very basic concepts in the quantum mechanics. So here I am Suraj, and let's start the lecture of the normalizations and expectation values. So here you can see I have written the Schrodinger wave equation, which is a very fundamental equation. So I have told you that when you solve this particular Schrodinger wave equation, what you will get is known as the wave function. I have said in my previous videos that you get the wave function when you solve this particular Schrodinger wave equation. So हमें क्या मिला कि हमने जब इस पर्टिकुलर इक्वेशन को सॉल्व किया तो हमें इसका एक सॉल्यूशन मिला जिसको हम लोग कहते हैं वेव फंक्शन. सो इस वेव फंक्शन की कुछ इंपॉर्टेंट प्रॉपर्टीज होते हैं, क्योंकि हमने कहा था कि जो क्वांटम मैकेनिक्स है वो प्रोबेबिलिटी पे बेस्ड होता है. तो इसका कॉन्सेप्ट ये है कि क्या प्रोबेबिलिटी है पार्टिकल को फाइंड करने का पर्टिकुलर रीजन में. सो इसका आइडिया दिया गया था बॉन्ड्स के द्वारा. बॉन्ड ने अपना इंटरप्रिटेशन दिया था. तो बॉन्ड के इंटरप्रिटेशन को हम लोग आज नॉर्मलाइजेशन के कॉन्सेप्ट से जोड़ के देख सकते हैं, बिकॉज बॉन्ड ने ये कहा था कि जब आप मॉड स्क्वायर लेंगे हमारे वेव फंक्शन का, और उसको अगर आप एक पर्टिकुलर लिमिट से इंटीग्रेट कर देंगे, जनरली माइनस से प्लस इन्फिनिटी तक, तो उसका वैल्यू 1 के बराबर आएगा. क्योंकि ये बहुत ऑब्वियस है कि सम ऑफ ऑल प्रोबेबिलिटीज इक्वल्स टू 1. तो 1 कहने का क्या मतलब है कि पार्टिकल जो है वो स्पेस में एग्जिस्ट कर रहा है, उसका पूरा प्रोबेबिलिटी का सम माइनस से प्लस इन्फिनिटी तक 1 है, यानी वो कहीं ना कहीं स्पेस या फिर कोई रीजन में वो एग्जिस्ट कर रहा है. तो इसलिए प्रोबेबिलिटी फाउंड करने के लिए बॉन्ड्स ने अपना इंटरप्रिटेशंस को दिया था. तो वी आर गोइंग टू राइट द हियर द इंटरप्रिटेशन गिवन बाय द बॉन्ड, which says that when you integrate from minus infinity to the plus infinity of the mod square of the wave function, its value is equals to the 1. So this is known as the Bond interpretation that gives us the probability. It means you mod square the wave function and you will get the probability for finding a particle from a given limit, and for a space we take it from negative to the positive infinity, and it is equals to the 1. So what actually normalization is? What happens is that it is not necessary that always when you integrate the wave function square from minus to positive infinity is equals to 1. It is not always possible. So we multiply it by some sort of constants to make it 1. And the process by multiplying some of the constants to the wave function square so that it when we integrate it, it become 1, what known as the normalization. It means it is not necessary that always this is true. It is true. What happens is when you multiply it, let's say that I have imagined a wave function whose when you mod square it from minus infinity to the positive infinity is not equals to the 1. So I multiply it by some sort of constant so that it becomes 1. I multiplied by a constant so it's become 1, and this is what known as the normalization. Multiplying it by a constant to the wave function square so that it becomes 1. So this is the concept, that we just multiply it by some sort of constants, which can be written as here a square, and here wave function more square wave function mod square here. So here I have written that we multiply it by some sort of constant. So let's take example to understand this better. So I am here taking the example of the infinite square wave, and I will also teach you about the infinite square wave in the upcoming lectures. So for an example, I have taken any of the wave function. So let's say the wave function of the infinite square wave. So I'm here write here the infinite square wave function. So infinite square wave function is equals to the a, and here sine n pi x divided by a, and this is the particular wave function for the infinite square wave. So here you can see that in this particular wave function, it's a small constant called a. So this is the normalization constant. So this is particular normalization constant that we multiply it to the wave function, so that when I take the integral of it from the negative infinity to the positive infinity, it becomes the a square and sine square, a square sine square and pi x divided by a dx is equals to 1. So I have multiplied by some sort of constants, and this process is known as normalization, multiplying a wave function by some sort of constants so that it becomes 1 is what known as the normalization, and a constant is known as normalization constant. So I will tell you that for this particular wave function I have written, for this particular wave function the value of a is, I am going to write here that for this particular wave function I am writing here for this particular wave function, the a is equals to root under, this particular a is equals to root under 2 divided by a, and as usual root 2 divided by a as usual sine and pi x divided by a. And okay, so for this particular expression you can see here that in the place of a I have written root under 2 by a. It means I multiplied root under 2 by a to this particular wave function, so that when I integrate it from negative to the positive infinity or whatever the limit is, it's equals to the 1. So this is a small concept of normalization which is very important in the quantum mechanics. It's a very important in the quantum mechanics to understand the concept of normalization. Maybe the wave function is normalized. Not in all situation you have to normalize. Maybe it is normalized, maybe it is not normalized. If it is normalized, the value of a automatically become 1. But in this case, what we found that the value of a is root under 2 by a for the infinite square wave. So here I've discussed our small concepts of the normalization of the wave function, that what exactly the normalization is and what's normalization constant is. So the next topic is the expectation value, that what exactly the expectation value is in, and it is also related with the wave function with this particular Schrodinger wave equation. So we are going to discuss about our next topic called the expectation values. So here now the expectation values. So first of all we have to understand the expectation values, and then how we obtain the expectation values for the observables in the quantum mechanics. So what is expectation values? सो एक्सपेक्टेशन वैल्यू, तो यहाँ पे जो एक्सपेक्टेशन वैल्यू है वो एक स्लोपी लैंग्वेज है जिससे मिसअंडरस्टैंडिंग हो सकती है कि एक्सपेक्टेशन वैल्यू मतलब ये नहीं कि व्हाट्स द मोस्ट प्रोबेबल वैल्यू ऑफ द फिजिकल क्वांटिटी इन द क्वांटम मैकेनिक्स. दिस इज नॉट द थिंग. जैसे मोमेंटम को एग्जांपल लेते हैं, तो अगर मोमेंटम का एक्सपेक्टेशन वैल्यू कुछ आया तो इसका मतलब ये नहीं है कि वो सबसे एक्सपेक्टेबल वैल्यू है मोमेंटम का। इसका नाम एक्सपेक्टेशन वैल्यू है, असल में इसके पीछे का एक बहुत डीप मीनिंग है एक्सपेक्टेशन वैल्यूज के पीछे का। तो जनरली एक्सपेक्टेशन वैल्यूज क्या होते हैं? तो जनरली जो एक्सपेक्टेशन वैल्यूज होते हैं वो हमें बताते हैं एवरेज ऑफ ऑल आवर मेजरमेंट्स फॉर डिफरेंट डिफरेंट वेव फंक्शन। तो यहाँ पे दो डिफिनेशंस आती है, तो इन दोनों डिफिनेशंस में बहुत ज़्यादा डिफरेंस है। एक तो पहला है कि लोग एक्सपेक्टेशन वैल्यू को ऐसे इमेजिन करते हैं कि एक्सपेक्टेशन वैल्यू जो है वो आपने जितने मेजरमेंट किए क्वांटम सिस्टम पे, जितने मेजरमेंट किए क्वांटम सिस्टम पे उसका एक एवरेज होता है, उसका एक मीन होता है। नहीं, एक्सपेक्टेशन वैल्यू ये नहीं होता है। एक्सपेक्टेशन वैल्यू होता है एवरेज, आपने जो मेजरमेंट किया अलग 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 स्टेट क्वांटम स्टेट्स यानी अलग अलग वेव फंक्शन का, एक ही पर्टिकुलर सिस्टम को बार बार हमने ऑब्जर्व, एक ही पर्टिकुलर वेव फंक्शन पे बार बार हमने मेजरमेंट्स किया और फिर उसका एवरेज लिया, वो एक्सपेक्टेशन वैल्यूज नहीं होते। एक्सपेक्टेशन वैल्यू होते हैं एवरेज ऑफ ऑल द मेजरमेंट्स ऑन डिफरेंट डिफरेंट पॉसिबल क्वांटम स्टेट्स, बहुत डिफरेंट डिफरेंट क्वांटम स्टेट्स यानी डिफरेंट डिफरेंट वेव फंक्शंस, डिफरेंट डिफरेंट कह सकते हो सिस्टम्स, डिफरेंट डिफरेंट उसके, जैसे एक पर्टिकुलर हमारा वेव फंक्शन है, एक पर्टिकुलर हमारा सिस्टम्स है, उसके बहुत सारे प्रोबेबल क्वांटम स्टेट्स हो सकते हैं। तो एक्सपेक्टेशन वैल्यू होता है कि जनरली उसका एवरेज, अलग अलग क्वांटम स्टेट को आपने मेजर किया, यानी आपने उस पर्टिकुलर पार्टिकल था वो किस किस वेव फंक्शंस में एग्जिस्ट कर सकता था, आपने उसके एक ही पर्टिकुलर सिस्टम पे बार बार मेजरमेंट्स नहीं किया, आपने उसके हर अलग अलग प्रोबेबल सिस्टम्स पे आपने उसको मेजरमेंट किया और वो सबका आपने एवरेज लिया। दैट इज व्हाट नोन एज द एक्सपेक्टेशन वैल्यूज इन क्वांटम मैकेनिक्स। दैट इज व्हाट नोन एज द एक्सपेक्टेशन वैल्यूज इन क्वांटम मैकेनिक्स। सो कैसे हम एक्सपेक्टेशन वैल्यूज को लिखते हैं और इसका क्या कनेक्शन ऑपरेटर्स के साथ? So now how can we write the expectation values and its connections with the operators? So in our previous lecture we have discussed about the quantum operators, that there exist a quantum operators which acts on the wave function, we have taken the example of the momentum operator. We take the example of the momentum operator. That's momentum operators means its action wave functions and gives us the information about the momentum of the particle. So the expectation value, or sorry, the operator of the momentum can be written as the negative of the iota h cut del divided by del x. So this is the operator. This is known as the momentum operator. So when it acts on the wave function, it will give all the information of the momentum. So now straightforward we are talking here. स्ट्रेट फॉरवर्ड हम जानते हैं कि आखिर क्या होता है। जनरली मैंने कहा था कि वो मोमेंटम के ऑपरेटर्स एक्ट करते हैं वेव फंक्शन पे। आखिर कैसे एक्ट करते हैं, वो जो हमारा एक्सपेक्ट वैल्यू यानी एक्सपेक्टेशन वैल्यूज होता है मोमेंटम का, उसको हम लिखते हैं कैसे? तो जनरली मोमेंटम के या फिर कोई भी पर्टिकुलर ऑब्जर्वेबल्स के हम लोग या फिर फिजिकल क्वांटिटीज़ के क्वांटम मैकेनिक्स में एक्सपेक्टेशन वैल्यूज़ को लिखने का, एक पर्टिकुलर डिफाइन करने का एक वे होता है। जैसे कि हम एग्जांपल लेते हैं मोमेंटम का, तो जैसे हम एग्जांपल ले मोमेंटम का, तो एक्सपेक्टेशन वैल्यूज को हम लोग ऐसे दो ब्रैकेट्स के अंदर डिनोट करते हैं। जैसे हमने ऐसे, तो एक्सपेक्टेशन वैल्यू ऑफ मोमेंटम इज इक्वल्स टू द इंटीग्रल फ्रॉम नेगेटिव इन्फिनिटी टू द पॉजिटिव इन्फिनिटी psi complex conjugate, psi star, we can psi star, it means complex conjugate, and here p operator, and here the wave function dx. So this is the way you can determine the expectation value of the momentum. Here I will explain this. This first term is known as the complex conjugate of psi. This first term I will write it here, that this is the wave function. Okay, so this is psi, known as the wave function, and when you take its complex conjugates, when you take its the complex conjugate, this is known as complex conjugate of psi. This is complex conjugate of psi. So what is the meaning of the complex conjugate of psi? As we all know that wave function is complex, it contains imaginary part iota. So we have to take its complex conjugate so that our observables can be real. Remember, in quantum mechanics, observables are real. Observables are real. So we just take the complex conjugate of the psi and sandwich the momentum operator between them. As you can see here in this equation, this is momentum operator I defined here. So this is a momentum operator, this is the wave function's complex conjugate, and this is the wave function. So this is the way you can write down the expectation value of momentum or any of the dynamical quantities, So let's say for position, how can we write? So for position, how can we write? So for position expectation values, we can write it in a similar manner as an integral from negative infinity to the positive infinity of the negative infinity or the positive infinity, and here the complex conjugate of psi, here the x operator, and here the we write psi, and last dx, psi into the dx. So this is the way you can write for the expectations value of the position. So this is how you can write the expectation values of the position. So for any dynamical quantities, you can write down like this. Like for kinetic energy, you can write in a similar manner. You just put the kinetic energy operator middle and sandwich between the wave functions, complex conjugate, and the wave function. So this is the exact meaning of the expectation value, and this is, and it also has a derivation how the momentum expectation value is equals to the this particular thing. So this is the part of the probability. As you know that quantum mechanics is probabilistic, so you have to know some of the probabilities. So in the next video, I'm going to derive the expressions of the expectation values, that how we derive the expression of the expectation values from the probability part. From the probability part, we are going to derive the expectation values. So but in this video, we are going to study the meaning of expectation values, that how we can write the expectation values of any of the dynamical quantities, the sandwich between the wave functions, complex conjugate, and the wave function. And for any of the variable, maybe kinetic energy, potential energy, and whatever the particular thing is, we can write down like this. So I will give an example of the momentum and the position. So here you can see that in operators, this particular momentum operator. So how can we derive this particular momentum operator? So yeah, there is a derivation of this particular momentum operator. So the most easiest way is that from this Schrodinger wave equation. How we can derive from this Schrodinger wave equation? So first of all, writing this Schrodinger wave equation, I will try to derive the particular this operator. No, yes, momentum operator. So here we can write this Schrodinger wave equation as the negative h cut square divided by 2m del square psi divided by the del x square plus the potential as a and equals to the iota h cut del psi divided by the del t. How you can derive? So if you have watched my previous lecture, I have told you that this particular expression is known as the kinetic energy operator. This particular expression is known as the kinetic energy operator if we leave the wave function. So we can write down that momentum operator, sorry, the kinetic energy operator. So from kinetic energy operator, we will derive the momentum operator by the simple relationship. So this is the kinetic energy operator. If we leave the psi, then particular this terms becomes the kinetic energy operator. So how you can write this as? So kinetic energy operator is equals to the negative of the h cut square and divided by 2m, and here is del square upon del x square. So this is the formula of the particular kinetic energy operator, particular kinetic energy operator. So how this is a very important expression. So I'm going to derive this particular momentum operator from this very important expression of the kinetic energy. So this is a very important equation. So remember this. So because this equation will going to just here. Okay, so how can we derive this? So in classical mechanics, there is a formula of relating the kinetic energy and the momentum known as the kinetic energy is equals to the p square or the momentum square divided by the 2m. So we can use this particular formula to derive the momentum. So if we know here, we know that the we just put here the operator sign so that we are dealing with the quantum mechanics. So what's the expression of the kinetic energy operator I have written? So the expression of the kinetic energy operator I have written is minus h cut square and divided by 2m divided by 2m and here del square upon del x square. So this is the expression. So this is equals to the momentum operator square divided by the 2m divided by the 2m. So I will cut down this particular 2m and 2m from this equation. So after this you can see here what will remain left is that momentum operator is equals to the root under of this particular quantity. It means it is equals to the root and so it is equals to the root under of negative is a negative sign negative h cut square and del square upon del x square. So we can simply just put out this here and we will get the expression of the momentum operator. So momentum operator is equals to the, so first of all this h cut square become h cut del upon del x del square upon del x square become del upon del x and left is the root under -1. So what is root under -1? So this particular expression root under -1 is known as the iota. So this particular term root under -1 is known as the iota. So here we put root under and after the root under what we will do is that after the root you can see that we will plus minus both. We should lead the plus minus both. So the thing is that it would be plus minus all the terms come out and then root under -1 becomes the iota h cut and del by del x del by del x. Here is the thing is that it should be plus minus, but in the most common sense we take the momentum operator as the negative. Remember the convention doesn't matter most in the physics, but it should be defined with some other relationships. So the most probable way of writing the momentum operator is in its negative form, as it is very it behaves very good in the simple quantum mechanical systems and all that things, but in the different types of the wave solutions maybe this is positive. Let's say if I remember it is in the plane wave the momentum operator can be defined as the positive, but our most possible conventions can be to just write this momentum operator as the negative of the iota h cut del divided by the del x or the partial derivative. So this is the derivation of the momentum operator from the kinetic energy operator. Similarly, from the momentum operator you can define the kinetic energy operator and also the angular momentum of the particle if it is revolving, or if in the next lecture on the more advanced quantum mechanics when we learn about the hydrogen atom, Then there will be discuss about the angular momentum, that how we define the spin of the particle. How can we define the spin of the particles, relation angular momentums, and all the quantum numbers. So I'm going to upload this in when you study deep quantum mechanics. So this is the video where I have discussed about the normalizations of the and the expectation value, that why we have to normalize because this may be not equals to 1. Also the expectation values, that what exactly the expectation values are. Expectation value is a very sloppy language. So this is a video where I have discussed about the normalization and the expectation value. So hope you will like the video, and in the next video I'm going to discuss about the uncertainty principle and other videos on solving the wave equations, Schrodinger wave equations for the infinite square well, for the step potential, for the Dirac potential, and different types of things, Dirac functions. All of the things we are going to discuss in this particular series of the quantum mechanics. So if you have any doubt related to this particular topic, or you have any question related to this particular topic, let me know in the comments if you have any doubt. So thank you for watching my video of this expectation values and the normalization. So thank you.